I'd like to talk to you a bit more about frictional forces. So far, we've talked about the fact that this is a force that occurs between two surfaces, and this force opposes the motion. We've also discussed the fact that friction acts in a parallel direction to the relative motion. In this example here, we see the man pushing to the right, and the direction of the crate is to the right. It is in motion. Whereas the frictional force is acting in the opposite but parallel direction, opposing that motion. The frictional force is the leftward force of the road on the crate in the above example. What we haven't talked about is the fact that there are two types of friction, at least that we'll discuss in this course. There's static friction and kinetic friction. Static friction, denoted with a subscript of SF, occurs when an object is stationary, i.e. not in motion, whereas kinetic friction occurs when an object is in motion, and you can see it is denoted with subscripts K and F for kinetic friction. You need to understand that these frictional forces actually arise from interactions on a microscopic level. So here I have zoomed into this crate, and you can see these ridges and valleys, if you will, that are occurring on the microscopic level. Well, in order for an object to be set into motion, there has to be a force to overcome these ridges and valleys. And so that is actually where friction comes from, is from microscopic interactions. Here is the formula for the force of friction. It is equal to a constant or coefficient of friction, mu, multiplied by force normal. We're going to talk a lot about this particular equation. I call it the physics is fun equation because, as you can see, physics is fun. Now, of course, that's not a U, that's the Greek symbol mu, which is used, but it looks like fun to me. Now look at your College Board equations sheet. You will see something similar. You will see the physics is fun written as an inequality. I'll expound on that in the next video. You'll also see the modulus bars, which indicate that we're looking at the absolute value, so we're not going to worry about signage. I will also talk to you about this in the next video. So, moving on to talk more about these types of friction. When talking now about mu, it is the coefficient of friction. And what it is it's a proportionality constant, and it depends on the two materials that are in contact. Now recall that schematic I showed you on the microscopic level. In that case there, it was the surface of the crate rubbing against the surface of the ground. So it is a property of the interaction of those two surfaces. You guys, mu is actually calculated experimentally, and you're going to be doing that in an upcoming lab. Mu is also dimensionless. What does that mean? Look at the physics is fun equation. I want you to algebraically solve for mu in your head. Notice how you're dividing the frictional force by force normal. Recall the derived unit for force is a Newton. So if you're dividing a Newton by a Newton, that cancels out. You're left with no units. Therefore, mu is dimensionless. And it typically ranges from 0 to 1. There are exceptions. There are two types of mu, as you may have surmised. We have mu for static friction, and we have mu for kinetic friction. Now remember, static means not in motion. Kinetic friction is when the object is sliding. Those values for this proportionality constant are different when we're looking at static friction versus kinetic friction. So the force of friction turns out, is directly proportional to force normal and also to mu. You know, I talk about this anytime I introduce a new equation. So as you can see, if we were to look at the proportionalities between these two, force of friction is directly proportional to force normal. If force normal doubles, force of friction doubles. Likewise, if the value for mu, that interaction between those two surfaces, for some reason were to double, perhaps by moving an object from one surface to another, then force of friction would also double. They're directly proportional to one another. Let's look at this object, which is at rest on a surface. Let's sum the forces vertically for this object at rest. We will call up positive and down negative. Now, because this object is at rest, it has no net external force and therefore no acceleration. Right side becomes 0. We can rearrange this, solving for force normal, saying that force normal is equal in magnitude but opposite in direction to the force of gravity, which is the product of the mass multiplied by the acceleration due to gravity. Why am I doing this again? Here's why. Because if force normal equals mass times the acceleration due to gravity, then we can take this fact here and we can put it into the physics' fun equation. You're going to be doing that a lot for objects, and it's important to remember if force normal equals mass gravity, we can plug it in. And later on, we'll talk about what force normal equals for objects that are, say, on an incline. We'll talk about that coming up. So, looking now in the x direction, I want to talk to you a little bit about the force of static friction. Now, recall I said this is when an object is stationary. So I am summing forces in the horizontal direction. This man is pushing to the right on the crate. The force of static friction is opposing that motion, even though the crate is not moving. That's what static friction is. So I've defined to the right positive, to the left negative. The object is not accelerating horizontally. Therefore, the force applied by the man on the crate is equal in magnitude, opposite in direction to the force that the road applies to the crate, which is parallel and in the opposite direction, and that's the force of static friction. All right? What I'm trying to show you here by summing the forces is that that applied force will be equal to the force of static friction until the object is set into motion. Now, we can again look at the force applied being equal to, physics is fun, so force of static friction, we can take this and put it right there. And we can also take the fact that we know force normal is equal to mass times the acceleration due to gravity. So we can make that substitution as well. So, as you can see here, both of these frictional forces, kinetic and static, are dependent upon the contact surfaces, which determines the coefficient of friction, mu, and also force normal. Now, look at this scenario. We now have two objects, and I'm going to define these two objects as a system. I'm going to say each has a mass of m. Therefore, in this second scenario, my system has a mass of 2m relative to the first scenario. I also have my coefficient of static friction indicated. Now, why am I showing you this here? Well, I'm showing you this because if force normal increases, then, as I've said, force of friction will increase, and that is directly proportional. So in this case here, what's happened to force normal? It's doubled. It's now twice the magnitude it was in scenario 1. That means that the static friction now has also doubled in magnitude. Now take a look at this schematic here. The top example, we have a small force normal. The second example, we have a large force normal. It goes back to those microscopic interactions between the two surfaces. But if force normal is increased, then those surfaces are going to be pushed together, and therefore it'll be harder to set the object into motion because of those opposing frictional forces. So when we looked at force normal here, we're looking at right here the upward force of the road onto the two-crate system. So it is analogous to this bottom example. It's like pushing down onto this crate. By putting a second crate down, we have increased the force of friction by way of increasing force normal. It's like pushing down on the two objects. In fact, you could push down on an object and you are increasing force normal. You're increasing force of friction if you increase force normal. So in this video, I've given you an introduction to the two frictional forces we'll discuss in this course. In the next video, I'm going to expound and we're going to look at examples as well as look at this graphically. I'll see you guys in class.